Uh, let me see. Okay, okay, perfect. Yeah. Uh, Sorry for the issue. So we temporarily solved the problem. But it's not gonna uh, happen again. But we don't know. Eventually, I still need to fix the problem somehow. Okay. Anyway. So where do we leave off? We end up at e- um the equation in the form of quantity 4n squared plus 4n plus 1, and then minus 8m squared equals 1. So this is in fact exactly the form that we want, because now we group the two things. For everything inside parentheses, we see that it is in fact the perfect square that we expect. Okay, which is again is square of the quantity 2n plus 1, where on the second part, the 8m squared we can rewrite as 2 times 4m squared, uh, which is equal to 1. And of course, we want the right side to be 1, right? But then, more importantly, the 4m squared part we can rewrite as the quantity uh, 2m, the whole thing squared, like so. In order to match the form uh, x squared minus 2y squared, which is equal to 1, as we want. So here is the complete sketchwork. So this is what we get. We have uh, 4n squared plus 4n plus 1 rewrite into the square of 2n plus 1, which is some kind of x. And again, we are saying that both x and y are just positive integers, right? Or natural numbers. But then 2n plus 1 is in fact a specific type of natural numbers that in fact it will be an odd natural number. Okay, so or it will be an odd number. So in this case, we our x has met, which in particular is an odd number, not an even number. Where on the same time, the y part will turn into the 2n that we actually solved when we rearranged the equation, where showing that y in this case will always be even numbers. Okay, so this is how we actually complete our sketch work to get what we need. Okay, so here comes the actual proof. So suppose uh, uh, how can we say it? Um, so basically, the sketch work is actually quite close to our final answer. So suppose that, or we can say let A be a square triangular number triangular number uh, uh, such that A is equal to m squared, which is again equal to 1/2 uh, n squared plus n for some. In this case, again, we assume that we're talking about positive integers. We don't worry about, well, 0 is technically will be the zeroth term of the square a square number and a triangular number. One is always the first term in this case. But then of course, for now we're dealing with positive integers, so don't worry about being zero. So in this case, we have um, m and n are some positive integers or natural numbers. Okay. Then by rearranging the above equation, we get, now here comes the sketch part. Oops. So we don't need this, and actually we don't need this either. And then, yeah, so we have from the beginning like this, which is of course equal to, this is a little bit annoying when they actually get something, oops, if and only if, okay? And then we will actually get the if and only if for both sides. Or we can just do something extra like this. Then we have if and only if, like this, and then of course we don't really end with the last part, because it doesn't make sense when we suddenly turn the m and n into x and y without any explanation, right? So we can just try to kind of like add the proof here. Let's say we get this. Oh, oops. This one I should actually have a shift here. There we go. Which shares the form x squared minus 2y squared equals 1 by taking x equals 2n plus 1 and y equals 2m, satisfying what do we have? Satisfying x and y are positive integers, again, or natural numbers. And again, this is so clear that because we have x equals 2n plus 1, where 2n plus 1 we have shown that as an odd number, of course, it's a natural number, and y is equal to 2m is an even number. And of course, it's natural number because both m and n are natural numbers or greater than 0, or positive integers. So the products will be even even positive integers, and the other one will be all positive integers. But either way, it's still showing that it's a positive integer overall, and that's how we actually get our solution done. Okay, so here we go. This is our complete proof. Good. So now we are moving on to part B. The curve x squared minus 2y squared equals 1 includes the point 1, 0. Let L be the line through 1, 0 having a slope n. Find the other point where L intersects the curve. Okay, so now we actually need to use the high school algebra tools to try to help us solving this equation. Now, once again, what does that mean? We of course have to write something like beginning proof, or what is it? Oh, it's a solution. Okay, we need to find a solution. So here we go. Do we need this line? Yeah, we actually kind of do need this anyway. We're gonna give a little bit of space here. So here is a sketch work again. Here's a sketch for part B. Recall that a line or linear equation on the 2D plane, x or xy plane, can be written as a slope form: y equals mx plus b. Okay, so our squared word would be, we have the form y equals mx plus b. Okay, now notice that y equals mx plus b actually satisfies, equals mx plus b, um, passes through point, let's see, point 1 comma 0, right? So in this case, we actually know the one of the x-intercepts, or actually the only x-intercept for a linear equation. Okay, then we can substitute in, and of course to find out what the y-intercept is. Well, of course, in terms of m. Okay, so uh, we're going to do a quick substitution. Okay, uh, and in this case, we have the substitution of x equals 1 and y equals 0. So we have 0 is going to be equal to m times 1 plus b. Okay, that means that b is going to be equal to negative m. So we can just jump to the results right away. If we try to write it into, well, slope form, of course we get that mx plus b. But another way of saying it is we can write as the x-intercept form, which is actually giving us something like this: x minus 1. Okay, so this is what we have so far. Now, of course, we're saying that this point actually includes this, and the L is a line that actually passes through this. Find the point that intercepts the curve. So we actually need to do a substitution there. Okay, so recall that, let's see, in this case, we assume our x and y to be positive. Well, I mean, uh, if we try to look at the graph itself, let's try to open GeoGebra here, or decimals. So decimals. We have a free Guardian calculator here. So let's share this. So we have x squared minus 2y squared equals 1, which actually looks like this. It's actually a hyperbola that opens sideways. And then, of course, we actually have, let's see, we are going to add another equation here, y equals m times x minus 1. So it'll always pass through, and then we're going to add a slider like this. Okay, so we actually can kind of see that, let's see if there's any setup here where actually L intercepts the curve. Okay, where L intercepts the curve. So uh, so in this case, we actually will see that the other points we have is something like here. Okay, 3 comma 2 when m is equal to 1. Okay, of course, if we have our slider change, in this case we can actually have something like very close, and then we could also have the m to be negative, so that it might actually hit the negative side, or yeah, negative value or maybe positive value like this. So we can have, let's say, for example, we have, let's say if we have something like right here, then we see that when m is like at 0.6, the other points we have could be actually ending up in the negative side when both x and y are negative. Okay, and of course we can also have something like, let's say if m is negative value, let's say negative 4, well, negative 0.4, we actually will end up with the other points on will be on the fourth quadrant, no, the second quadrant, which again is showing that the x value here will be negative instead of having a positive x. Okay, good. So now we're going to substitute back into our equation there. So what we need is, now we need to find out the x and y values would be for the other points. So as we have this expression out, we can now try to substitute. Let's solve for x first, meaning that now if we continue working on it, we are going to replace the y in the curve the curve equation, x squared minus 2y squared equals 1. We're going to replace this y by the quantity and well, I'm going to factor out, or it's okay. We can leave it as it is. Okay, we have this this monster here. X squared minus 2 times the quantity m times another quantity x minus 1. Okay, this entire thing is squared. Okay, not including the 2, of course, equals 1. Okay, so or might as well just trying to kind of multiply that out instead of factoring the m. Let's just leave it like this. So we're going to get something like m here. We don't need this. So this is what we actually would get. Great. So now what is our goal? Well, our goal is to solve for the other the other points, meaning that we need to solve both x and y. Like for the coordinates. So in this case, we're going to solve for x first. So if we do that, we of course we get something like multiply we have x squared minus or factor that thing out, we actually or multiplying that thing out, we're ending up with 2m squared x squared. And then we will have minus times minus actually turning into a plus. We have 4m squared x, and then last but not least, we have the m squared, so it will be minus 2m squared, something like this. Okay, and then which is equal to 1. And now we are going to regroup the x squared parts. So if we do that, we factor the x squared, we actually end up with 1 minus this thingy times, well, 1 minus 2m squared. This quantity multiplied with x squared. So let's refresh it a little bit, and we actually get some what we compile actually they call. So now we can use the quadratic formula to help us getting the value of x. So if we do that, of course, our old friend quadratic formula says the top is negative b, where b here is 4m squared. So we end up with negative 4m squared, and then plus or minus the square roots of b squared. So b is 4m squared. The square of it is going to be 16 times m to the 4th power. And then we are going to subtract 4ac. So we see a negative, so it turns into a plus. And then 4 times 6 is giving us 8m squared. And then times the a value, which is something like this. Okay, and then of course we still have 2a in the denominator, so we get some gigantic fraction like the following. And let's see if we can actually try clear up the thing inside the parentheses. So if we try to multiply out we actually get 8m squared minus, well, times 1 is, of course, 8m squared. And then minus 8m squared times 2m squared. That's going to give us 16m squared. So we'll get something like so. See how it looks like. Okay, great. Meaning that's now, oops, not square, fourth power. Again, that's because we have 8m squared times 2m squared. M squared times m squared is the fourth power. Meaning that now we can in fact try to cancel out the 16m to the fourth power to end up having just simply 8m squared inside of the square roots. So we recompile it and we actually get something like this. And we can, of course, try to factor something out inside of the square roots. In this case, we can actually factor out the 4m squared to leave the square roots of 2 inside. Oh, well, it's just 2 inside the square roots. And then for 4m squared, if we factor out and take the square roots of it, we end up with just simply 2m in front. Okay. So we got something like this. And the good thing, here's the good news. We can actually factor the 2 on top and then cancel with the 2 on the denominator such that we have the new fraction, new expression of this fraction like the following. We have something like this. Great. So how come x equals 1 is always a solution here? Well, we can kind of see it that if we set x equals 1 here, we should end up with, let me see. If we always get x equals 1 as our one of the solutions, and we can substitute back in and see that in that case we actually would get 1 is equal to plus or minus m over m times square root of 2, or square root of 2 of times m, meaning that if we square both sides, we always get m what let's see. Oh, actually, we don't have to. We always have m is equal to some other some other stuff here. We how should I explain it? So if it does not well, okay, here is the reason. Because the point 1 comma 0 does not depend on the slope m here. So if we try to substitute in, we actually will see that for particular m here, when this case, if we set x equals 1, then what we actually will get is that 1 minus 2m squared is equal to 2m squared plus or minus m times square root of 2. Meaning that if we do that, we actually will get m is equal to plus or minus 1 over square root of 2. But in that case, we actually will get something very interesting. So again, we're going to use decimals to see how the graphs actually look. Okay, go back here. So we have x squared minus 2y squared equals 1. Okay, good. Then for a second equation, we have y equals, again, we need to set our m's. In this case, we have mx m times the quantity x minus 1. So we have one of the uh, um, one of the what's it called? One of the slopes or n values is going to be positive 1 over square root of 2. Okay, and then of course x minus 1. And then the other one is going to be negative version of it. Negative 1 over square root of 2 x minus 1. So let's see what is going to happen in these two graphs. Okay, let's go one by one. Let's say if we have the positive slope. Okay, let's zoom out. If we zoom out, in fact, what we get is we have only one solution. Yeah. So how come it only has one solution? And in fact, this line would be an asymptote. Well, it's approximately an asymptote of of what we have. Again, what's the asymptote of the curve? It is in fact y equals just the slope times x without the minus one part. Okay, that these two and plus or minus version will actually give me the two asymptotes of the curve, and now we have the shift of the asymptotes. And this is actually saying that well, if we try to um, again use the asymptotes to take a look at the graph there, square root of 2 times just x here, and then I'm going to get the negative version, negative 1 over square root of 2 times x. Okay, so if we now hide just hide the equations we found. Okay, if we look at these two asymptotes, can I change the color? It actually doesn't look good. Um, setting minor small options. Can I even change the color? Hopefully I can change the color. It will look easier to see. No, not here. I think it's here. Delete. Oh, no. It's okay. It's okay. Anyway, if we look at these two asymptotes and try to zoom in, we can kind of see that, of course, when it's close to the origin, it will not cross the curve. But even if we try to approach to the infinity on whatever end we have, we still see that it will never touch. It will get closer and closer, but it will never touch the curve, meaning that these two asymptotes, linear asymptotes, y equals plus or minus 1 over square root of 2x, these two asymptotes has no intersection with the curve that we have. Okay, and therefore, if we try to shift those linear equations 1 unit to the right to give us these two lines, we will not be able to get any point passing through um, the curve except the points that is already given here. Okay, and this is why this going back to our this is the reason why this expression actually makes sense. Why m cannot be equal to 1 over a square of 2 and negative 1 over square of 2. Otherwise, we will not be able to find the second point here. Okay, so we just end up with something like this. Again, this m is actually not a fixed slope for us in this case. Then and of course there we're assuming that m as a slope is a real number here. We are now considering the vertical line x equals 1. Okay, in that case, of course, if we go back to the graph once again, if we try to go back to this graph, if we have the line x equals 1 with the slope m does not exist, or you can think it's like positive or negative infinity if you want to think it that way, then of course clearly it will only touch the point 1 comma 0, and then it will not give us any other point. Okay, so other than the situation of vertical line, and when x or when m is equal to plus or minus 1 over radical 2, uh, we will actually be able to get a second point for where the x value of that second point will actually be the following. Now, you might question, how come we actually get two different values? Okay, well, because we actually don't know what m is, and if we know the m value is, we actually will be able to consider one of them to be positive one for sure. Okay, um, and then the other one will just turn out to be the points that we're looking for. Okay. So is there any way that we can actually find out that will always give or will always get positive or negative one? Actually, not really. And once again, that's actually depend on what the slope is. So sometimes when you do such kind of problem, we just need to be a little bit careful. But so far we'll just leave it as our answer. Now, back to the problem itself, we're trying to find the other point, meaning that we also need to find the y coordinates of the point um, that passes through the both of the line and the curve. So in this case, we need to go back to our equation y equals mx minus m and do a rearrangement. We're gonna rewrite the equation in terms of x. So of course we have x is gonna be equal to we're going to divide both sides by n first to get y over m. We have fraction y over m. And then, of course, after that, we have a plus 1. We just add the 1 back, well, move the minus 1 to the other side to end up with plus 1. So that now we actually see that the shift of x based on the linear equation. We actually have something like this. Okay. Hopefully this is not going to affect our results. Okay, good. Where did they go? Oh, down here. Okay. So keep in mind, starting from here to here, these are the two separate results, because now we're trying to find, we're going to stretch for to find out the y value. So in this case, now we're going to substitute back into our equation here, x squared minus 2y squared equals 1. So if we do that, of course, we will end up with x is replaced by the expression y minus y over m plus 1, and then we have this quantity squared. Okay, and then we have minus 2y squared, and then which is equal to 1. All right, great. And again, we're going to multiply both sides by m squared, or all terms by m squared, so that we'll actually end up with no fractions for now, so that will be easier for our calculation. So we end up with m y plus m quantity squared plus minus 2m squared y squared equals m squared. There are a lot of m squares in this expression. And as we factor out or multiply out, we actually end up with y squared plus 2my. And again, in this case, the y is our variable, m is playing as a role of constant in this case, plus m squared, and then minus 2m squared y squared equals the right hand side, which is just m squared. Now you will notice that there are a lot of things. There are a lot of nice things that can be cancelled out. So, for instance, if we do so, we actually will have um, first of all, we have the m squares being cancelled out, and then we can factor out the y square for the first term. So we end up with something like this: y squared equals y squared times the quantity 1 minus 2m squared. Okay, or we can just put it the other way around. Okay, times the quantity square, and then we have plus 2my. It's going to be equal to 0. So we actually end up with something like this. Okay. Now, in this case, it will be even easier to solve for y than for than solving for x, which we actually need to use the quadratic formula, and then trying to do a lot of algebras to actually end up with two possible solutions. In this case, we actually will see that there is exactly one solution. Again, why? Because now if we try to factor the y, we will get the following. So if we factor the y, the first term will just turn into 1 minus 2m squared, this quantity times y still. And then for the second part, it will just turn out to be 2m, which is equal to 0, right? Now, here's the tricky part. You remember when we try to solve non polynomials? If we can factor out something in our polynomials, then when we try to solve the equation like this, we will just set each part to be 0 as a possible solution. So in this case, we actually get to two parts: either y is equal to 0, or the other parts, everything inside the brackets, is equal to 0. Why does it matter? Because we want to remember the goal of this problem is to find the other points, where the first given point is 1 comma 0. In this case, the y value is equal to 0. So whenever we want to find the other points, we will assume that y is going to be the part that is not fixed to be 0. And then we will just use that as our y value, meaning that we can ignore y equals 0 as our option, and we will just leave the parts inside brackets as our part of the our solution. So in this case, if we solve that, we actually will get everything inside of brackets is equal to 0. We'll just throw the 2m to the other side to turn into negative 2m, and divide by everything inside parentheses to actually end up with negative 2m over 1 minus 2m squared. Now, we can try to multiply both top and bottom by negative 1. You're trying to get off the negative. And now, of course, on the bottom, we'll just turn into 2m squared minus 1 instead. So that, in fact, will give us the y value. And that is the missing y value that we want. Okay. Not here. Perfect. Okay, so that is the y value that we actually want. Okay, we avoid we try kind of avoid the option that when y is always equal to 0, which actually implies that x is always equal to 1 in that case. How? Because we actually have the linear expression here, x is equal to y over m plus 1. So now we can just use this and substitute back into our equation to see that x is going to be equal to this fraction over m. So in fact, this fraction is 2m. So the m and this m and m will be cancelled out. So we end up with just 2 on the numerator, and then denominator will be 2m squared minus 1. And then don't forget there's a plus 1 at the end. Okay. So now we are actually we actually get a fixed value. Well, not a fixed value. We actually get a certain results for x instead of having two options. Okay. Now, where did this come from? Well, we can try to bring the x back in. bring the 1 back in to the fraction to get 2m squared plus 1 and then plus 2. So actually we get something like this. How come it looks different? Well, that is because now we actually solve with y and then trying to solve for x. Instead of having solve for x and then ending up with a lot of mass here and then possibly 2 different results. So this actually completes our proof here. So let's try to go back and where is it? Here. So we're gonna go back to this line starting from x squared minus blah blah blah, and then we're going to clear out this thing so that now we actually get something for something that we need. And then we actually get a very nice and neat solution here. Perfect. Very good. So again, do we really need where can we start off? We actually don't really need the first 3 lines. We can rearrange it as well. But eventually we actually get the x and y coordinates, okay, of what we have or what we need. So here is the actual solution after the sketch work. Okay. Let y equals m times times the quantity x minus 1 be the line through 1 comma 0. And again, that with slope m. And again, we're just following from the question itself. Okay. Then that makes everything a lot clearer. Then we're gonna start from here. We have, oh my god, where'd it go? There it is. We have y equals mx. Well, we're saying we actually factor down. Okay. So this is gonna be equivalent to, and again, we would just put all the if part here. If and only if, by the way. My bad. We will actually get this. Or we can change to implied. It doesn't really matter, honestly. They mean almost the same thing because it's just algebra. So we get something like following. So we have starting off with our expression y equals m times quantity x minus 1, and then we're going to get what's going on here. Oh, this is good. This one doesn't look that good, but anyway, implies that y is x is equal to, we divide both sides by m first to get y minus y over m, and then we're gonna add 1 on both sides to clear out with the x in the explicit form. Then we can say if and only if, because it's actually formed from the previous line. Now here in the third line, we have to use implies. Once again, that's because it's not following from the second line, but it's actually a combination from the second line, the linear expression, the explicit form of x in terms of y, and the curve that we have, x squared minus 2y squared equals 1. And then what we did is we're going to replace the x in this curve equation by y over m plus 1. And once again, I'm not sharing, sorry. Okay, so this is what we actually get when we clear out. Okay, once again, we actually will get something like the following. It's actually up here. Very nice. So we actually have something like yeah, y is equal to this if and only if again we just mentioned just basic algebra. And then for third line, we actually need to do a substitution. We are using the well to the curve that's given, so we cannot just say if and only if anymore. Yeah, and after that, we're going to have yeah, everything else will be if and only if. Oops, like this. And then if and only if. Yeah, and then there's just a lot of algebras here, but then we can actually we're not gonna skip the algebras in between. Otherwise, it might be hard to to follow up. So we actually get something like this. Let's see. And again, eventually we actually get something like this. So the entire structure is going to look like this for the solution. So we actually get y is equal to this equal it implies that what if and only if x is equal to that, and then substitute in, and then we do all the algebra works. Square no multiply both sides by m squared. Then we're going to multiply out everything inside of parentheses, and then have the cancellation of m squared, and then we're going to group the two terms of y squared together, and then after that we actually can factor out the y, and then here uh, for the y part, I'll change the symbol to implies. And again, why do we not take y equals 0 as our option? That's because we in our setup we don't want um, we don't uh, we don't want y equals 0 as the only solution because we want to see what happened for the other points where y might not be equal to might not be always equal to 0, and or in other words, for the other points that we have, the y value we hope that is not always equal to 0. We hope that it's gonna be dependent on the slope, and we actually see that from the graph on the decimals that if we change the slope, the y value of the points that's being intercepted will also get changed and it's not always equal to 0, meaning that it's actually dependent on the slope of the linear equation that we have. Similarly, once we solve it, we actually can solve for x, and then we actually will get the results we need. So then we have um, so we can actually make a conclusion here. Therefore, the uh, other point, let's see, what's the question asking? The other point where line L be the line L. Okay, we're going to mention it here quickly. Um, where line intersect intersects the curve. Well, they usually call it L or C, whatever, but they didn't label it. Who cares? We already know what the curve is. Is now we're going to put down the x and y coordinates together as a point. Okay, so what's the x coordinates? Well, the x coordinates that we get will be 2m squared plus 3 divided by 2m squared minus 1. Actually, minus 1. Sorry, this is a typo here. Here is a small typo. It should be a plus 1. Did anyone notice why? Well, I'll leave as a question down below for you guys to figure out. Okay. And then for the y value, we have 2m over the quantity 2m squared minus 1. So that completes our answer for part B. This one actually takes a little longer. That's a good question. Hopefully I pronounced your name correctly. Is it your? Um, this is technically the second or third year of math in university, and in America. Well, it depends how fast you take the courses in college. Some students might be very smart, and also this course, when I took it in my college or in university, um, there was technically no requirement or no prerequisites. Until later on they changed that to have prerequisites of set theory and also hi Maya. Um, so in fact, whoever wants to take the course, well, at least in the university that I was in, whoever is who is interested to take the course, uh, can actually take the course back then. Now they have a requirement of knowing how to passing the set theory course, which is actually more like a introduction of how to write a proof, because they actually found that a lot of people don't really know how to write out a proof that is easy for reader to follow up or understand. But anyway, other than that, anyone can take it. Yeah. So yeah. Now, of course, we're trying to write it as a formal proof that it follows logically and all and stuff like that. Anyway, yeah. So we actually get the results that we need, which is down here. Good. So there are still four parts. Hopefully, we can finish it by today. I'm going to speed up a little bit from now on. Okay, part C. Suppose that you take m to equal m equals v over u, where v is a solution to another equation or curve equation, u squared minus 2v squared equals 1, which actually looks very close to our expression and no x squared minus 2y squared equals 1. And again, that's like trying like replacing with another variable. It's, throwing in a different graph. Yeah. Hopefully you guys enjoyed it. But either way, I'll still continue working on it. And of course, if you're interested on taking the course, it'll be a it'll be great. And this is actually the textbook that I used when I took the course in university back then. Um, and I'm trying to work out all the well, hopefully work out all the problems, and then uh, so that you like whoever is trying to uh, study this course, especially using this textbook, you can actually try to use my solutions or answers as reference of how to how to do the problems there. So back to the question. Show that the other point that you found in part B has integer coordinates. Further, changing the signs of the coordinates if necessary. Show that you get a solution to x squared minus 2y squared equals 1 in positive integers. And that actually makes sense too, because again, when we are trying to look back to the setup of m values, we can have positive, we can have negative, we can have m equals 0 as well. Of course, we actually exclude the option of m equals plus or minus 1 over square root of 2. But then other than that, there's nothing to stop us having m to be negative, which is also showing that the other points that we have from the decimal graph, um, will actually give us the other the coordinates of the other point would be negative for x or negative of y, or maybe like they could be lying on the other the other quadrants other than quadrant one. Okay, and of course that's not going to affect that much to the um to our results of x and y being positive, because once again, if a negative value of x works, then the positive value of x should also work when we substitute back into the to the linear equation, or not the linear, to the graph itself. And usually this is actually based on once again the m value of m being positive or negative. Okay. So what are we supposed to do here? Well, let's see. If we try to do oops, bad habits here. If we are trying to do that, we're going to show that the other points you found is so we actually have something like a answer. Usually I would like to call it the solution, or maybe, well, usually I like to call it a proof, but technically it's not really having a nice setup of proving it. So what we have is now we're gonna uh, substitute in m to be that. So showing the other point you found in part B, so we have given m equals v over u. Uh, then uh, for the other point, for the coordinates of the other point, oops, points. Again, the expression is this big fraction here. I'm going to copy and paste, make it faster. Okay. We can rearrange, oh, not submit, substitute, substitute, uh, did I spell it wrong? Yeah, substitute with a T at the end. Substitute to get. So here it comes. We have this big chunk here. Let me put left here and right there. Yeah, right there. There we go. I'll put an equal sign to get something like this. Or maybe I should just use one equal sign, I guess. Yeah, one equal sign. Oh, well, no, one. Oh, okay, one n sign. It's good. Which actually, if we substitute in, we have here replaced by v over u, and then we have v over u again. Down here we have v over u, and down here we have v over u again. Which in this case we can multiply both top and bottom by u squared to try to get rid of the complex fraction here. So if we do so, we will end up with getting rid of the u square, we have just 2v square and then plus u square. And then here, of course, we have 2v square minus u square. And then for the other parts, we have u and u square will actually cancel one of them to leave another u. So we have 2uv, and then on the bottom, we still have 2v square minus u square. Okay. Okay. So this is giving us um, the other point that we found it has an integer coordinates. Okay. So if we substitute back in, we actually get the other points that we have integer coordinates. So how do we see it? Well, we kind of, because what we need we can actually we somehow need to multiply the denominator back to the equation. So what does that mean? Well, uh, because again we have the setup of u square minus 2v square equals 1. What does that do to our expression? Well, if we pay attention to our denominator, in fact, we can factor a negative to give us u square minus 2v square. Agree? Which, in fact, we can replace everything inside the parentheses by positive 1 based on our expression. So here is an intermediate step. If we try to do a replacement, or factor a negative 1 in the denominator, and then we are going to do a replacement or substitution of our setup u square minus v square equals 1, we actually end up with the denominator to be negative 1 only. And of course, the top part there is always an integer because u and v are integers. So wherever we do, as long as there's no division there is always an integer. Thus, we can actually, in fact, rewrite the both fractions into just simply negative, an integer, negative u square minus 2v square. I don't need this part. Great. Minus 2v square. And then for the second part, of course, we just have negative 2uv. Good. And this is exactly what we're hoping for. Let's see. Let's recompile it. See what we can get. I think we're missing something here. Oh, here. I need to press one more. That's why it looks kind of a mess here. It's all crammed up between the problem and the answer. Let's recompile it. So we actually get the expression down here, and unfortunately, for some reason, we actually will see that's the both x and y values are negative here. But anyway, it's not going to affect our calculation too much here. Because our goal is for this first part of the this first sub part of the problem is showing that uh, showing that the other point has integer coordinates. Now, of course, for now, the both coordinates of this point is negative, and this is why in the second part of this question says further change the signs of the coordinates if necessary, um, so that we actually turn out both x and y positive, showing that you get the solution in positive. So what we have is by multiplying both coordinates by -1, we obtain uh, what's it? Positive u square plus 2v square, comma 2uv uh, be this be a solution to the original curve 2 x squared minus 2y squared equals 1. The well, we can kind of name it original curve um, in positive integers. Now again, this is actually a little bit tricky in some sense. We actually we can by multiplying if needed. Let me put it if needed. We actually obtain this absolute value. And here's the reason why I actually put absolute value there, because we actually don't know if the end up result is always positive or always negative. There's no guarantee. Okay, it could be initially the negative version. Well, um, the negative version is positive if we have some setup of v is negative and u is positive. Again, there's no limitation between u and v besides knowing that u and v are well are solutions of to that equation there. Where of course we're assuming that u and v are just integers in this case. But we can have v to be negative and u is positive, so that we actually have you know or we can have 2uv. The product of 2uv is negative, so negative 2uv is positive. That's why we would just put absolute value sign in case that like we don't know which one is positive or which one is negative. We just forcing them to be positive in this case. Okay. um, to get to the solutions of what we really need. Okay, so part D. Starting with the solution 3,2 to the curve, apply B and C repeatedly to find several more solutions to the curve. Then use those solutions to find additional example of square triangular number. So now we're actually back to part A. Yay! We're now going back to find out more um, square triangular numbers. Okay, and again, we can actually try to use part B and part C to help us to find find more solutions to the equation. Well, in this case, we actually can see that what we need is u squared plus v squared, and then 2uv here. We can now try to assume that both u and v are positive, such that we are now able to get more solutions to the original equation. Okay. Um, and once again, uh, so in that case, if we use this result here, we can have, for example, well, we already choose u and v to be equal to 1, such that we have the x coordinate is 3, y coordinate is 2. Um, so we can actually try to, let's make it like 3 or 4 more. Okay. Well, let's try to make 3 more then. So here is our answers or solutions. So in our solution, we have, let u equals, let's say 2. Well, we actually need to avoid something though. What we really don't want is that uh, u and v, well, u is even. Well, of course, we shouldn't assume that u is even, because in this case, if we have u is even, then we actually get the x value to be even, and y is always even. So we'll recall that x is always odd. We actually have to set u to be some odd numbers. So let's say u is equal to 3, and then in this case, we can have, let's say, and v is equal to 1. Then we get uh, the solution, solution where the x value is going to be u squared plus 2v squared. So we have 3 squared plus 2 1 squared, comma, and then we have 2 3 1. And that is going to be, if we solve it, we have 3 squares 9 times 2 plus 1, 2 plus 2 times 1, which is 2. So we get an 11 for x coordinate, and then for the y coordinate we get 6 here. And of course, we should double check our work. Okay, so is that going to work? Well, let's see. If we throw in if we throw that in, x squared is going to be 121 minus 2y squared, which does not work. Okay, so in other words, it's not always working. Okay, we actually need to be very careful when we try to do the calculations. Okay, so in this case, it actually doesn't work. So what else can we try? Well, we can actually try to use the m values there. Well, we have to force ourselves m to be equal to 1. No, not necessary. If we choose something like m equals 2, no, that's not going to work. So let's try to pick something something harder. Let's say we're going to stick with u to be 1, and then right, again, because we actually have to have conditions of between u and v. So in fact, what we need is, let's say if u is equal to 3, then v has to be equal to 2. My bad. So in that case, we actually will get something like this. That makes more sense. So if we apply it, if we have u is equal to 3, then we have 3 squared, which is 9, plus 2v squared, where v is 2, which is v squared is 4, so 2v squared is going to be 8. So we have 9 plus 8, which is 17. And then for the other coordinates, we should end up with 12. So let's double check real quick. 17 squared is 289, And then 12 squared is 144 times 2 is 288. So if we actually have the subtraction, we do end up with 1. So this one is actually working. Perfect. Then next we have we can just keep repeating this game. Let's say if we pick u is equal to 17, then we can have v is equal to 12 because we actually repeating this process. Now, is there any way that we can actually avoid this? Well, we already said that uh, if u is equal to 1, v has to be equal to 1 in order to avoid, we actually had the negative version of it. But this is how we actually get the first solution. Now, if we choose something like u is equal to 3, but then we won't be able to get -1 because we have 2v squared is going to be equal to 10. So this is this is not what we want. So let's say if we have u equals 5, then we end up with 25. 25 minus 2v squared is equal to 1 or -1. So we either end up with 24 or 26. Okay, or actually no, 24. Let's see. Well, clearly 24 doesn't really work. And then let's see. Yeah, if it's 24 or 26, none of them will actually work. So in fact, it will be easier if we keep sticking with these values. So let's say let's u is equal to 17 and v equals 12. Then we get the solution. Now again, we're going to get something like this, very similar, but then it will get a lot bigger if we continue this game. So we have 17 here, we have 12 here, and 17 here, and 12 here. So what do we get? Well, we have 17 squared is 289, and then the other one is 288. So if we double 288 plus 1, we get 577. And then for the other one, we have, what is it? 34 times 12. That is going to give us 408. And then let's stay with these two. Okay, if we keep going, the numbers again larger and larger. Okay, so now we're going to use these two these two examples to find our additional example of triangular numbers. Okay, how do we find it? Well, recall that in part A, um, uh, we actually have uh, we actually have x is equal to 2n plus 1 and y is equal to 2m, where where m is actually the square roots of the square triangular number. So we're gonna stick with the y. Well, we can actually stick with the n. The y part is actually giving us a lot something easier. So we actually see that if we do so, we have this implies a square triangular number is gonna be square of the half of the y value, which is again equal to 12 over 2 all squared, which is equal to 6 squared, which is 36. Okay, and we actually can check that this is also a triangular number. Okay, because if we substitute into with the with the x value parts and then throwing it back into our um formula of triangular numbers, we actually will get the same results. Okay, so we can see check uh, the x. Oh well, we can actually have n values is equal to uh, what is it? Uh, we start off with x is equal to n plus one, so it will be x over two, the entire thing minus one. I know this expression doesn't look nice. Let me uh, rewrite it. This look better. It is actually less uh, well, we don't we will have more agreement of what this is going to be solidly. So in this case, we actually get well, what is our x value? We have 17. So throwing it back in, we have wait a second. Oops, my bad. I did make a mistake. It will actually be this. So throwing back in, we actually get 17 minus 1, which is 16. All over 2 is 8. Implies that, what is it? Uh, 1/2 of the quantity n squared plus n, n, is going to be equal to, again, we have 1/2, 8 squared, 1/2 times 8 squared plus 8, where 8 squared 64 plus 8 is 72, divided by 2 is giving us 36. Good. Now, similarly, if we try to play this big one here, which I'm not going to check the work, by the way. Otherwise, it's gonna take a long time to do all the calculations. Well, this is already long enough, but we actually can somehow handle it. So we have y over 2 quantity squared is going to be equal to, again, we have 408 divided by 2. That's going to be 204. And then if we square it, we end up with 41616. Okay. Now I'm gonna leave the verification for you guys. Trying to figure out if this number 41616 is a triangular number. Okay, I'll leave it as an exercise for you guys. So here is our solution. We have our solution down here. Perfect. So part E, prove that this process leads to infinitely many different square triangle numbers. Well, answer. So basically, what we did is we're taking the previous one to going to the next one. Notice that in parts, I'm going to answer it in a tricky way. It's a little bit sneaky, by the way. The process can continue by induction. Thus, it leads to infinitely many different square triangular. I misspelled it again. Triangular. Triangular. That's why I made a mistake here. That's why I made a mistake. Okay. Triangular numbers. Perfect. All right, great. Now, part F, which is the last part. Prove that every square triangular number can be constructed in this way. This part is very difficult. Don't worry if you cannot solve it. So, excuse me. Well, in order to prove that this works, first of all, we need to understand why this process will work. But if we try to come back to um, the entire problem that we actually start off from part, well, not let's not say part. Well, we actually do need to go through from part A. Okay, this every part of this problem is actually trying to lead us how to generate the solution. Okay, um, that will actually make it work. But if we trace back all the way to part C, we actually see that now we're guaranteed to have to have a solution, positive integer solution based on this setup here. Um, well, and most likely we'll just pick u and v to be positive values, so that in this case we don't even need the absolute value sign. We actually will just contain um, x equals u squared plus 2v squared, and y equals 2uv, and then it will actually guarantee us to actually get the proof. Well, not the proof, guaranteeing us that we'll actually get the set of the number being a square and a triangular number simultaneously. Okay, because of again because of the curve uh, uh, u squared minus 2v squared equals 1. Okay. Now, of course, we can somehow try to analyze this part here. Not completely, but we can try to analyze uh, the setup that we need for u and v, because we want u and v to be a solution to the curve, where the curve itself uh, is actually the same as the curve that we have, where u and v are positive integers that we actually start off with. So therefore, uh, what can we say? As we assume that u and v are positive integers as far, well, we can kind of explain it this way. Well, no guarantee that is completely true though. Here's our answer. Well, it's kind of like a proof. Well, it's not a formal proof, but you guys can think it as an informal proof. As uh, I'm gonna put a note here, by the way. Formal, informal proof as we choose u, v be positive integers or natural numbers that satisfy uh, the curve u square is equal. Oh, not minus one equals one. For the solution, x again. Um, what do we want? X is actually equal to 2n plus 1. 2n plus 1 is equal to x of m and where we're gonna start off talking about what m is, by the way. Um, m is equal to uh, well, or 2m is going to be equal to y, which is equal to, and again, what's our y value? Y is going to be our 2uv. If and only if m is going to be equal to uv, and now we have 2m plus 1. Oops, no. Hold on. 2m plus 1 is equal to x, which is again equal to what do we have? X, no, sorry. U square plus 2v square. For some u, of course, we want our u to be with u odd, okay? And again, we don't really care, well, we don't really know if, well, in this case, we satisfy, okay, for satisfy this notes u is must be odd and v must be even. Now the proof of this, we can go back to chapter 2 and actually we can kind of see it. Why u has to be odd and v has to be even in this case. um, anyway, this actually guarantees that for the n part, implies that n is going to be equal to fraction u square minus 1 all divided by 2 and then plus v square. If and only if actually implies. It will be better if I just say implies. Here's the thing that we're missing. Where m and v are m and n are these expressions, and this is going to guarantee us that where this is, let's see. Wait, hold on. How far am I? How far am I at? Can we consider it this way? So we actually need to do the calculation, or actually you need to do the substitution too. So let's see what we have. We have this here. So we have we chose what our u and v be, and then in this case we have something like how should I say it? We can actually somehow simplify this. So let me see. Oh, in fact, I just realized what we can actually, in fact, try to replace um, replace the u square in terms of v square. So in fact, we can get something like, to make it simpler, or just make it depends on v only. We actually get this thing is going to be equal 1 plus for v squared. Why does it matter? Because now if we try to solve for n, we take away the 1, and then we actually get n is just simply equal to u uh, no yeah 2v squared. Then let's see where this is. Let's see. As we choose for where this we obtain the square triangular number in the following ways. With m such a number becomes, now we're going to verify it. We have m squared, which is of course equal to the quantity uv squared, which is again equal to u squared v squared. But what's u squared and v squared? Well, what's u squared? Well, based on our setup at the beginning, this is going to be equal to 1 plus 2v squared, okay, times v squared. Okay, now with n such number becomes, this part is a little bit tricky. So in fact, I actually get a formal proof, not just an informal proof anymore. We'll see why. Oh, no. Oh, there we go. Okay. With n, such number becomes okay, we're almost done with this problem. We have, using n, which is a triangular number, we have 1/2 n squared plus n, which is, by substitution, we have n is going to be equal to what? 2v squared. Okay. So we're going to put it like this: 2v squared plus 2v squared and now I'm going to factor out the 2v squared. So if we factor it out, we have 1/2 times 2v squared. And then for the remaining part, we have 2v squared plus 1. Okay. Of course, where's the equal sign? There we go. Of course, we can actually cancel the 2 from the 2v squared with the 2 in the denominator to end up with just v squared times 2v squared plus 1, which again we can rearrange it as 1 plus 2v squared times v squared. And and we actually I don't need this row. I don't need this row either. And we end up with the same expression as we desired. So here is the formal proof and actually the complete proof here. Because after we do the substitution, we should expect these two will actually end up with the same results, so that we actually get the same number to show that this result here is in fact a square and a triangular number at the same time. And this is what we need to do, and we actually did it, and therefore we actually get what we want. All right, we finally finished chapter 3. So, and also it's already past 2 hours live stream. Well, actually, if we take away the 10 minutes that I try to fix the technical issues, it's actually all exactly 2 hours. So we'll actually end here, and one, two page. Okay, yeah. We'll actually end here, and next time we're gonna start off chapter 4, and we can actually try to skim through it. It looks like there are only 2 problems, but then we have to actually write quite a lot of things here, and then hopefully it's not going to spend too much time on it. Hopefully we can finish the entire chapter by in 2 hours next time. If not, we probably need to again get another get another episode. Right. So that is it for today. Thank you everyone for watching. I'll see you next time.